Hey there. So in this video, I'm going to talk about a very important topic, that of multi-objective optimization in the context of performance marketing. So all media buyers, all of us who are into media buying actually face this problem whenever we are tackling objectives which have trade-offs. So for instance, if we want to maximize revenue and we want to maximize ROAS, which is of course what we want in every case, there's actually a conflict, right? Because we know because of the concept of diminishing returns, as we try to increase spends, there is an upward push in revenue, but only up to a point, and then it starts tapering off, depending on where the point of saturation really is for that business, for that set of channels and all that. And the ROAS also tends to drop. So there is a conflicting sort of a relationship between ad spends and ROAS, and similarly between revenue and ROAS by extension. So what to do in that case, how to take decisions like, for instance, budgeting decisions, budget allocation decisions among channels. So suppose you're spending on a number of channels, how do you want to decide how much to spend on which channel? This is something that actually boils down to something called a multi-objective optimization problem. And this is purely mathematics, and it can be done using code. So generally what happens is media buyers take these decisions in a very manual sort of a manner, very haphazard manner, just looking at data over the last few days and taking decisions based on that. But that's generally not a very good idea. The best idea is to approach it scientifically in this sort of an approach. So what we'll look at is basically called the multi-objective optimization problem. We'll define the problem statement and we'll talk about the solution. So the solutions that we get is basically called Pareto solutions, which lie on something called a Pareto front. So we're going to look at all of that. And this is basically going to be looking something like this. For instance, I'm showing you the final product. So this is the Pareto front. These will be the best set of solutions, right? So there are going to be other solutions marked here by the blue points, for instance, which are called the feasible solution space. But that those solutions are not necessarily not better than the ones than the red ones that you saw over this line. Okay, so we are going to arrive at the Pareto front. These are going to be the decisions that So you have a set of possible decisions that you can take, decision points, and by decision points I mean different ad spend allocations among the channels that you are running ads on. So that is what you really need. You don't just need one or two points because that may not be feasible, that may have limitations, and that may not work in other ways. But if you have a set of feasible solutions, then you can sort of test between them and test among them and see what works best. So this problem in itself is very mathematical, as I said in the start of the video, and there are a lot of advanced algorithms. I'm just going to touch upon them, as in what are the options that are existing out there, um, like evolutionary algorithms and all of that. So I'll just touch upon them. This is largely a subject which is, predominantly taught in computer science engineering and operations research, to be specific. But we're not going to really go deep into all the algorithms and stuff. The objective here is to have a practical, actionable solution for media buyers. And this Google Sheet is basically a done for you one-click sheet, which is going to help you solve this multi-objective optimization problem. So all you have to do is there's actually an app script that is running at the back end here. So this is basically entirely part of this function here, as you can see, which is called the generate feasible solutions function. And this is the function that is doing all the trick here. So you just have to run it from here from the back end of app script by jumping into this Google Sheet that I will be sharing in the description of this video, and then it should be good to go and it's going to do its work. So in terms of inputs, you will have to provide the search spend and the social ad spend. So this is basically done in this way that we are considering two sets of channels. One is search, SEM, and another is PPC, and another is social. But this can be defined in any way, right? Any channels. This can be like, for instance, Google and Facebook, or any way you want to decide. And in fact, it does not necessarily have to be channels. It's just two different inputs. It can be two different campaigns also if you want it that way. And then it's like the maximum budget. So for instance, what is the budget constraints? You will obviously have an upper limit so that at any given point in time, the maximum, the sum total does not go above a certain limit. So for instance, if you're taking 500 and 500, that's not a feasible solution, right? Because that's not a feasible data point or a feasible alternative, because that's above the maximum budget limit that has been set. And then you also have to provide a few things like, for instance, the search maximum revenue, the social maximum revenue, search efficiency, and social efficiency. Now, these are important parameters. These are basically defined in the context of that multi-objective optimization problem. And all of this actually has been discussed in a Notion document. So I'll just quickly uh, give a glimpse into the document here. This is also going to be shared in the description. So this is where I describe the problem and the different things that are there. So the initial section, so how it has been organized is first I've given the key features of the optimization problem that is in this code that's working at the back end of the Google Sheet, where I've talked about the different things. I'll just touch upon them quickly. There's the actual aspect that's been used there for your reference. Then step-by-step method how to use this script. Very simple. It's actually already been done most of it, but you can just go through them once more. What are the different input variables? So this is the part that I was talking about, and these columns here. So you have to give in. You can provide any number of values here, and just have to provide one value for each of these other columns apart from the spends. And then apart from that, the implication of changing in each input, that's also important. And then there is an underlying theory, which is just not, you know, limited to what has been provided in this sheet and this app script, but what other algorithms exist. That has also been discussed, and we'll quickly touch upon that. Now, coming to this goal sheet here, so maximum budget has already been discussed. Search max revenue and social max revenue. So if I just jump into this Notion doc here, so the way optimization problems work is that there's something called decision variables. So those are the variables that actually have an impact on the outcomes. So by optimization, we simply mean we want to maximize revenue and maximize ROAS, right? That's the whole point. So the decision variables in this case are the ad spends of the channels. And then there's a constraint. The constraint, as we have already discussed, that the sum total of these ad spends cannot be more than a certain threshold. So that's given by the max budget that has been given here. And then you also have a revenue function limitation. Now, the revenue function is basically that revenue that's getting generated. And this is basically the diminishing returns uh, curve or the diminishing return relationship that has been assumed. So like we said at the start of the discussion, and like we all have experienced as media buyers, that there tends to be a diminishing returns thing. And the exponential relationship, as you can see, between revenue and spend here, that actually ensures that it's a diminishing returns curve or relationship. Now you can see that there's a max revenue here and an efficiency here. So that's the whole point. So the revenue is going to be determined whenever you're talking about any particular channel, sorry. Then what happens is this max revenue remains the same for that particular channel. So this is basically the saturation level. So this is that level of saturation that you can expect from that channel in terms of the returns. Now, you may ask, how do you know this? So ideally, what happens is you should have already got this sort of a relationship with you where you know what is that saturation level beyond which it starts to drop. This is arrived at using something called a marketing mix modeling or a regression model that you have run previously. Okay, so that's usually the first step, and then comes the optimization step. Now, that is a pretty detailed step and a pretty involved step as well, and it's not very easy to show. It's not very easy to just do it in a one click and all. So that's a relatively involved step. Even if you're doing something like a regression thing can actually be done in Google Sheets. I probably showed that before. I'll show that in the future as well. But for now, just assume that you have that data. In case you don't even have that, you can actually assume it. So there's actually no problem with starting maybe based on historical data. So you can start with an assumed figure as to what is going to be the maximum revenue, okay, that you can get from a particular channel. So you have the max budget, you have the max revenue for both the channels. And so, for instance, in this case, we expect that social is more scalable, like we've seen in many cases, right, than search. So that's why the max revenue is more in social. And efficiency is this parameter basically. It's entirely related to this relationship, this diminishing returns curve relationship, and this thing here, which is in the power of the exponential factor. So this is an important factor, and this has an impact on the revenue that gets generated. Again, this is something that you will probably arrive at after solving for that regression equation, but you can always start with any small numbers like these points. So the way it impacts is something that you will get, the way changing these, values impact is something we'll get in this section here. So all the definitions have been provided, the efficiency. Okay, and let's actually see the section on efficiency where it will be defined as well. We'll just quickly run to that section. Right. So search efficiency and social efficiency, like I was saying, they control the rate at which revenue increases with spending. Okay. And it's, as you can see in the exponential power, there's a negative sign, right? So that ensures the diminishing returns curve. I have shown in my previous videos the tool called Desmos. So you can actually jump into Desmos if you want to actually see, play around with that exponential equation. Just put in those values, plug in those values, and you'll see that, how the curve actually looks like. For instance, if it's like e to the power minus 2x or something, as opposed to e to the power 2x, right? So you can actually see that if you are that much interested. Otherwise, just, accept these things and uh, just go with the flow. So higher efficiency means revenue goes faster with spending, and lower efficiency means diminishing returns sets in more quickly. So if you feel that the it's going to reach its saturation faster, diminishing returns is going to set in faster, then you will lower the value of efficiency. Okay, so that is something you can check from historical data, right? And you can decide on these factors accordingly. So it's entirely in your control. See the power of this, the simple little one-click sheet here. You just have to jump into AppScript and run it to make it work. Is that it has so much flexibility, right? So you can control that diminishing returns equation completely, and therefore the ultimate budget allocation and the optimization decision. So it's there's a lot of control in terms of max revenue. Also, this is what I was saying, that it sets the upper theoretical upper limit of the revenue for each channel, and the higher values mean that channels can generate more revenue, but the rate is determined by efficiency. So these work very, very closely together, because as you can see, both of these are very important elements in the revenue objective function. So that's, so these are the couple of objective functions. The total revenue is search revenue plus total revenue. Revenue itself is governed by this equation, as you can see. So this is an extension of the objective function, you can say. And we have the decision variables already discussed, and then ROAS is obviously total revenue by total spend. And then comes the concept of Pareto optimization. So like I said at the start, there's something called a Pareto front, or a Pareto, which consists of all the Pareto solutions, which are not dominated by others in terms of both total revenue and ROAS. Okay. Now, this means that this part here that I was saying, these feasible solutions here, none of these solutions dominate the solutions that exist on the Pareto front. So what does dominating mean? So this is a very important concept in multi-objective optimization. And I'll just jump to that section here for easier understanding. So Pareto optimal solution is no, is a solution is Pareto optimal rather if no solution improves one objective without worsening at least one other objective. Okay, so I'm just reading out the description so that you can jump to these parts. So, right, if there are other solutions where at least one of the objective is better served, then it is already dominated, and therefore it cannot be called a Pareto optimal solution. Right? I hope it makes sense. Uh, and the Pareto front, like I said, is the set of all the Pareto optimal solutions. The feasible solution space consists of all the combinations of decision variables that satisfy the constraints. So we have defined the constraints. So this feasible solution space are all the other solutions. So this is also a feasible solution, by the way, everything that's on the Pareto front. Anything beyond the Pareto front is an infeasible solution. Okay. So for instance, this area here on the right hand side, in for instance the LM and so you can understand why these are infeasible, by the way. So you have a max budget, right? So you can understand that the ones on the right are very high revenue and very high ROAS. Right, so that makes sense because anything that is very high revenue and very high ROAS, mathematically, it comes out to be impossible because that's not going to satisfy the diminishing returns constraints, right? So that's, visually also you can intuitively understand that that's the correct outcome there. And as I said, dominance, a solution X1 dominates X2 if X1 is at least good, is at least as good as X2 in all objectives and strictly better in at least one. right? So that's how we define. It basically uses an algorithm to iterate over different possible solutions and tries to find out all the solutions which are dominant over all the other solutions, and dominance is described in this way. Okay, so there are two objectives, and it at least has to be equally good as all the other feasible solutions in both the objectives, and at least good in at least better than all of them in one. Okay, it can be better in both objectives, but it at least has to be better in one and at least equal in the other. It can't be worse off, right, in any other objective. So the mathematical concept that is going on here is simple. Like I said, if you remember what I just said, and if you just think about it intuitively, there's a trade-off, right? So if you try to improve one objective, there's the tendency of worsening the other objective, right? So that is what's really going on behind the scenes in this app script. Just wanted to give you that idea. So what happens is you just run that script. That's all you have to do. You have to give these inputs. I've described the inputs already. Then this is going to generate. This is the output it's going to generate. Okay, so it's going to carry out these iterations, and the algorithm that has been used here, by the way, is actually called a brute force algorithm. Okay, so as you can see here, and there's a description of it. It's a very exhaustive exploration. It's a very simple thing. And by brute force, it means that it evaluates all possible combinations of the system variables. So by that, I mean all the possible combinations of the different ad spends, and it comes up with the total ad spend from there. And then based on that, the revenue and the ROAS. And then so this is the total revenue and total ROAS, and then it determines whether or not it's a Pareto solution. Okay, so that's how it works basically. So it tries to go through all the solutions. Now this is brute, as you understand from the name itself. It's a crude solution. It's forcibly trying to find a Pareto solution by forcing the ad spends to be of certain values. And basically choosing all possible combinations. But this is, as you understand, going to be very, very computationally expensive when you're talking about a large data set, or when you're talking about a very comprehensive solution. So a much better solution is to go for more advanced algorithms. But that's why I said at the start of the video, I'm going with the simplest solution. And since there are only a few input values here, it was not that computationally expensive. Otherwise, it would have taken much, much longer to actually run this code and get the solution. Okay, so there are many more advanced algorithms apart from this. So, for instance, I've just discussed two or three of them. Evolutionary algorithms, these are actually inspired by biology of the natural world. Okay, so they are there in the field of computer science, and they've been around for quite a while. There's particle swarm, there's many other evolutionary algorithms or genetic algorithms, and one of the most famous ones here is NSGA2. There's the third version of this as well, non-dominated sorting genetic algorithm. And some descriptions of this are given here. You can just read through them. If you want to discuss further, let me know, or you can just read up yourself. But I've not gone into the details here, but I've given them for your benefit. Then there's a relatively easy one, which is the weighted sum method, which is a pretty simple method. If you just read it, you will understand. Similarly, there's another one called epsilon constraint method. So there are many other algorithms that are there, but I've only discussed and I've only used something called the brute force algorithm. Maybe in the future I'll also create. And this is, I actually have used more advanced algorithms, but that has taken quite a lot of work, and that's a much more advanced sort of solution, and it's completely done in Python. So in fact, the curves that I've showed here, both of these curves, there's two here, that are actually outputs of Python codes that I've run here, as you can see. So these are used using more advanced algorithms. So this is Pareto front using weighted sum. And in fact, that one is weighted sum, and this one is again brute force. Okay, so there's one advanced algorithm that I've shown here. So the weighted sum one, as you can see, it's creating the Pareto front. Similarly, the same problem, ROAS and revenue maximization, and then there's the brute force one here, right? So this is the whole idea. So if you look at the output, so the output is, you can actually just simply filter this output, and you will find out everything that's a Pareto solution. So this yes is Pareto means that these are Pareto solutions, the most optimal solutions, and then you get all the feasible um, solution space for the different budget allocation combinations. Okay, so but you will this is then a matter of judgment. So obviously you cannot probably go with just 0 and 50, right? That's too much of a low spend. Of course, the ROAS is great and revenues is optimal, but you will have to go with something that makes sense. And you'll see that all of these remain within the maximum budget limit that has been set of 600. Right? That's the whole point of this exercise. So you can change this around, you can play around with it, and you will find all optimal solutions, and these are the best solutions that you can get with the assumption that is following a diminishing returns cost. So that's the point. This has started with that assumption, and that's why all of these parameters here are feeding into that equation, that diminishing returns equation that I showed at the start, right? This one here, this is the crux of the entire thing that's going on, and it's very, very critical. I've discussed about response curves in a previous video. I'll link that in the description as well. So go through that. You can try to create that on your own, or you can run through an MMM process. Media mix modeling is going to become more and more important. Conversion tracking methodologies, the conventional ones which are touch based, is just not so much reliable anymore, especially when you're talking about bigger projects and a bit more higher spend, um, because there's a lot of noise, and it's going to be very difficult, going forward, to sort of pinpoint exactly using these tracking methodologies. Much better to rely on these foundational methods like MMMs, because of all the price-related regulations, all kinds of cookieless technologies, and all of that, right? So anyway, that's a different point. If you don't have access to MMMs, or you have not run that, or don't have those exact data, I've already said that you can start with some presumptive values at the start of this process, and then you will come up with a with all these outputs. So once you run that, so once the chart is available to you, once the table rather, they're also going to give you, this sheet is going to give you the Pareto front chart, a very similar looking chart as you can see from the ones that have been generated by Python code as well. So this is actually, this particular chart has been, rather this one has been generated using the AppScript code. So this is where I will stop. I'll do a hard stop because there's actually so much to go on in this field, in this domain. It's a very, very advanced sort of a field. So this is the general. This document, I definitely suggest you to go through this document as exhaustively as possible. This is a very large field. People can literally do PhDs in this field, but we are not here to do that. We are here as media buyers to figure out, um, you know, how to take the best optimal decision. But if you dive deeper, what's going to happen is you're going to be able to, solve more complicated problems and take better decisions, basically. So this is part of decision science also, to some extent, and you're going to get better at decision making if you understand this better. Okay, so that's the whole point of, this is, this MOO, or multi-objective optimization problem, where you're maximizing or minimizing functions subject to some constraints. They can be equality or inequality constraints, and then the decision variables belonging to some sigma, which is some feasible solution space. Okay, so those are the concepts here: Pareto optimal solution, Pareto front, solution space, and dominance. These are the important things. Go through some of the algorithms. I've not really talked about them here. It doesn't really make sense in an introductory video like this, but I've given them for your reference anyway. So that's where I'll do a hard stop. I know this has probably been a loaded one, but it is pretty easy to get started with this sheet, by the way. So it's not difficult. As I said, give reference of these other videos on response curves and some of the other related topics to this, and do go through them. And if you have any questions, do let me know in the comments, and connect with me on LinkedIn if you're not already. We can discuss further. And yeah, uh, thanks for watching, and see you in the next video.